good to go? Okay. Good afternoon. My name is Ed. I'm a scientist here at the Simon's Electron Microscopy Center, and welcome to the Winter EM course. This is the 12th offering of this course at NYSBC, and the second in this reverse classroom format. So today we're going to give you an introduction to the course and how we're framing the course. And then for those of you here, we'll give a tour of the facility if you wish. For those that are streaming online, after the initial introduction, we'll leave the live stream going, but you don't have to keep on attending. So once again, I'd like to welcome you to the New York Structural Biology Center. We're here in the Simon's Electron Microscopy Center area. And a lot of interest has been growing in the field of Cryo-EM. In particular, a lot of people consider Cryo-EM single particle EM, but EM is more than just that, and we'll get into that. And it was the 2015 Nature Method of the Year. However, we want to move the field from a niche method to a very usable workflow for others to use. And John Cocteau once said, art is science made clear. I think there's a little bit more art than there is in science in Cryo-EM in terms of the workflow end to end. Hopefully through courses like these and work done by other people, that we can give you the tools and concepts you need to really be able to make this, this tool useful for yourself in your scientific program. To frame the course, what we hope is that this is the start of a 16-week apprenticeship where we'll tell you a little bit about the 3 different modalities of EM, as well as give you some future methods that the field is moving towards, and give you some idea of what resources you have here at the center. And for example, as artists need to know their tools like paintbrushes and paints, we hope that when we're going into these topics that when you move forward, you'll be able to appreciate these tools and then make them your own. Because though you can use a screwdriver as a screwdriver, but you can also use it as a paintbrush. So there's certain things that it can be used traditionally, and there's certain things that you can extend it beyond. Ideally, you won't be using some for high-end microscopes like a screwdriver, but we'll get into that. A little bit about course logistics. There are 3 handouts. We have a questionnaire. If you haven't filled it out, please fill it out before the end. There are a few announcement and waivers. For example, at the center, there's more than just EM going on. This is one of the highest concentrations of high field magnets in the Northeast, and we do warn you to keep away from certain areas. For the course, you're allowed in mainly the public areas in the SEMC conference room. Note that there is ongoing research going on to the right of me as well as to the left of me. We also have a copy of the syllabus, and as you know, we're going to try to live stream this course. So there's a waiver here. So not that we're actively trying to videotape you or talk about anything sensitive, but it is being live streamed. If you go to our website, it is semc.nysbc.org/course. You can see this. There's been an addendum. Originally, we were scheduling this course in the seminar room. Now it's in the SEMC conference room. As I mentioned, the live stream, you can access all our workshops that are live streamed through youtube.com/nramsemc. And that might be handy in case you can't make it to one of these courses. If you do log in remotely, ideally, occasionally there'll be someone here that can look at this live chat. So you have questions along the way, you can use a live chat. Okay. I alluded to that this is the second year we're offering the course in this format. This format is a reverse classroom. Now, there are several textbooks out there, and there are several online courses that you can make use of. And so rather than reiterate basic knowledge that you can get elsewhere, what we hope is that you would see these courses ahead of time, and you come here, we can really expand on the topics and have greater interactivity. Right? So that's the whole purpose of this course, such that you would have interaction with experts that have used this particular tool day in and day out in their laboratories, and be able to extend it to make it really useful for you. There are other courses. Currently, we're basing our web course via the Grant Jensen lectures. Shores also has a course at the LMB that's online. So there's a lot of resources out there if you want to look at these online courses. Advantage of these online courses, you can pause, rewind, and then repeat and replay certain lectures. Okay, so class structure. For the month of January, it's going to be a little bit condensed. We'll have lectures on Monday and most Wednesdays, and after that we'll have normal format. For this reverse classroom format, the lecturer will give about a half an hour introduction. We'll have a long coffee break so there's interactions, because some of these lecturers are really eminent in their field and it'd be great to interact with them. And then the last part will be open-ended for discussions, and we hope that this is going to be a very interactive course, that you'll be able to ask questions, and then we can extend it beyond the natural topic. On Wednesdays, we'll have video screenings of the Grant Jensen lectures if you don't have another forum to look at on your own. Also, we'll have office hours, so you have particular questions, you want to relate the topic, you want to hear it again, you want to talk about your research, that's a good forum for that. Okay. Our course is going to be broken up to 5 main sections. Section 1, I like to call that the EM fundamentals. This is where we'll give you all the foundational knowledge you'll need to carry on. Then we'll go on to each of the different modalities of EM tomography, single particle, and 2D crystallography. And then the last section will be more of a traditional lecture approach, because these are not covered in any of our online Grant Jensen lectures. We'll have a few topics that were raised last year that people are really interested about, and these are topics that are actually still in progress. So there's not a definitive final statement and conclusion from that, but you'll hear a lot of different views and approaches on how we handle different challenges in the EM field. So I'm not teaching the course alone. We have a good team of instructors, mostly from our 9-member institutions, part of NYSBC. We have a lot of the SEMC operational staff, as well as staff here at the center that is working in the background to bring this course to you. So I'll introduce the topics and introduce the lecturers up and coming. Do you have any questions before I go on? Safety, anything like that? Okay. So going into EM, I think the best question to pose to yourself is, what biological system are you interested in? At the center, the New York Structural Biology Center, we're fortunate to have the 3 main structural biology techniques housed here: NMR, X-ray, and EM. And that has allowed us to really see the strengths and weaknesses of the different techniques. And moving forward, most likely you're not going to be using one technique in isolation. It's going to be in concert and collaboration. But at the center, a lot of questions we get depends on the system they're coming from. Some people say biology is organisms, and they're interested in tissue-based or neural networks. Other people are interested in particular cells. You know, for example, the scale of a cell is somewhere around microns, like 5 to 10 microns, maybe even smaller. Some people are interested in viral entry into cells, and then you're going from the micron level towards the nanometer level. And some people are interested in structure function studies when they get to the nanometer angstrom level. So the question of what you're interested in biology really is a broad scale. And so for EM, we can actually range from the atomic level all the way to the millimeter level. But as I mentioned, though EM can access this whole range, there are other tools that might be better suited for particular questions and a faster turnaround. And that really gets onto the first section of the EM course. And the first lecture will be taught in combination. I'll be joined by Ashley and Kelsey, very good technicians here at Electron Microscopy Center here, and they deal with user samples day in, day out. And they'll be able to tackle challenges in sample prep and biological EM. And really, I like to consider that, how do you make a sample EM ready? I alluded to that an EM can scan or span this entire range. An electron microscope is a microscope, and if you want to get higher and higher resolution, well, you just crank up the magnification. If you want to see an organism, well, you just lower your mag. But there's a catch in that you have to prepare the sample to be suitable for the instrument. And how we prepare the sample, one may not be able to look at the same sample at the micron level as you can look at in the angstrom level. For example, if you're interested in a cell in a tissue, you might decide to embed it, fix it, and stain it. In that case, you're going to be limited in the nanometer scale because the stain itself has a particular stain grain that's a particular size. You could go into cryo and look at it, but most of our microscopes that we use day in day out are transmission electron microscopes. So if your sample is too thick, you can't image it. And so there's a balance between how you prepare your sample and what range you look at. And then that brings in the question of which modality are you interested in. Just like there are different structural biology techniques, within EM there's different flavors of how you use an EM. From all these particular techniques, you can use the same microscope and you get a similar result in raw image, but how you process it and how you treat your sample is quite different. Moving on to the next section of the foundational series, we'll go into our tools of the trade. Just like an artist have paint brushes, as I said before, our tool is electron microscope, and Laura, staff scientist here, will tell you about the two main EMs, the TEM and SEM. If you just briefly look at an inverted light microscope, that's actually very similar to a TEM, a transmission electron microscope. A scanning electron microscope, SEM, is slightly different. But just as in a light microscope you have a light source and lenses, in our EM we have an electron source, perhaps it's a field emission gun, and our lenses are actually magnets. And so there's certain limitations to that. If you go on to one of our 300 kV microscopes, our electrons could be going down the column 2/3 the speed of light. So we tend to have a very, very good vacuum in our microscopes, and it also adds to some sample limitations. But microscopes are one thing. There's been a resolution revolution, as it were. You might hear that term used quite often, and that's because our detectors have gotten more and more sensitive. So we can take a 10-year-old microscope, whereas we might be sub-nanometer range, now we can go to near atomic range, and that's by just getting a better camera on it, so to speak. Also, concurrently, a lot of computation has gone along with that. So our tools of the trade tend now to be CMOS cameras. Before we were using film and CCD, but right now we have CMOS cameras that are actually direct detectors that we can directly detect single electron hits, and that has pushed the field. Not only that, is that some of our cameras are not just cameras, they collect movies, and we can do motion correction. And then towards that, the last lectures of the first section will be on Fourier transform and image formation, taught by our senior scientists, Bill and Angie. And I would liken that these lectures were really the mathematical basis of how do you get a 3D object from a 2D image. Because whether you're using your TEM or SEM, you will be getting a series of 2D images, and how do you reconstruct that to a 3D image? There are many different ways. Also, something to keep note at is our instrumentation is somewhat limiting. We can't necessarily sample our samples at infinite degrees and infinite resolution. So there is a compromise on how much effort and time you want to put into a data collection versus the end result. And hopefully through some of these lectures you'll get a basis on knowing resolution limitations as well as how to design your experiments. That's the first section. That will be the month of January, and as you see in your class schedule, that sometimes we'll be meeting twice a week. After we get the background out of the way, we'll really dive into the three modalities of EM: tomography, single particle, and 2D crystallography. And what people find interesting in each of these topics have evolved over the years. First up, we'll have David Stokes from NYU teach us about tomography. As with all EM specialists, they do multiple techniques. So David has done tomography quite a bit, helical reconstructions. He's also done single particle. So if you talk to any one of these EM people and everyone around, you'll notice that we've used a wide range of techniques, even within EM. Then Bill and Alex are going to talk about two emerging interesting flavors of tomography. One is serial section flip SEM. That's a dual beam, focus ion beam, scanning electron microscope, and as well as bring single particle techniques to tomography, such as subtomogram averaging, and that's how you can push tomography to sub-nanometer resolutions. And I liken tomography as a very good technique if you have a heterogeneous sample, or perhaps a very limiting unique sample. You might have, for example, you're looking at a cell, one cell is like identical to another cell, but its conformation or its state could be different. And in that case, it's not the same sample, it's a very unique sample. And therefore, you only have one of it. Therefore, you have to characterize that one. Traditionally, electron tomography is very similar to like a CAT scan, where you would want several different views of a particular object and you can back project it. And in a sense, what you do is you tilt your sample instead of, let's say in a CAT scan, where you tilt your sensor around and you can get a 3D reconstruction of a particular region of interest. So that's classical tomography. As I mentioned, dual beam, FIB SEM is really using one beam, an ion beam, to cut a little bit of a layer off, shave a little bit off of a block, and use the SEM to image that. And then you can get a 3D reconstruction because you're just marching in through a volume and scanning in. And you can see here in this movie, your resolution is limited by your XY, and then your Z is how thick you're slicing. But a lot of the sample processing and data processing techniques between these two methods are quite similar. As I said, this course is trying to move forward and introduce new topics to you within these different modalities. Something that we are really working on in the center and the field's moving towards is in vivo or in situ type of electron microscopy, and especially correlative microscopy. So as I mentioned, there are techniques where you can bring single particle techniques into tomography. Let's say you're interested in the nucleus. Traditionally, the nucleus is quite thick in the cell, and that's very hard to take electron tomograms from. What we can do is, using our FIB, is take a little bit off the top and bottom, basically thin your cells such that it's a sample amenable for classical electron tomography, take electron tomograms of it, and then from there you can apply single particle techniques. Here's an example of what's done in the center. Here's a particular cell in the grid. With an ion beam, we can shave off a little bit of the top and the bottom of the cell. Here's our different views of the windows into the cell that we've created. And we can collect a classical tomogram, and then from these images, we can either do normal reconstruction, or if you see repeating units, we can box them out and treat them with a single particle to really push resolution. The next topic, the next modality we go into is single particle. And the slide I showed a little bit before was about the nature methods. I think I have that slide coming up. The team of teachers that are teaching that is Joachim Frank. He's written a very good textbook. If you look on our webpage, we reference that as a very good textbook if you want to have a textbook to learn about EM. He's from Columbia. Then right across the lawn here, we have Amadei and Reza following up, and then Rich Height from Sloan Kettering talking about all single particle techniques. So Joachim will lead off, and we'll follow on many different topics from these junior faculty. And single particle techniques can, again, be applied to just TEM images as well as other types of images, not just electron tomography images, but from FIB SEM. So 2015, since this was named Method of the Year, a lot of interest is in here. I'll spend a little bit more time and go over the single particle workflow. So typically when people talk about Cryo-EM, they're really referring to single particle Cryo-EM. And in this particular case, you would have purified proteins or protein complexes, or they could be macromolecular complexes, for example, ribosomes. They're floating in solution, and we put it onto, if you think of EM as an inverted microscope, our glass slide, it's really a 3 millimeter metal mesh grid. We apply our sample to that, and what we want is to freeze it so fast to form this glass-like water, vitreous, vitrified ice, such that we can contain our sample, such that it preserves structure, as well as can survive in the vacuum that we put it in, which most of our electron microscopes run. So here's a visual representation of particles in this vitrified buffer. Take pictures of it, and the hope would be we have many different orientations of the sample that we can take pictures of it. Through tomography, we approach this by just tilting our sample through the full range. In single particle, we assume we have random orientations within our sample, and then that we can see many different views within an electron micrograph. Here's a cryo-electron micrograph where we have electron-dense protein complexes on a vitrified buffer background. single particle workflow works as that we box out like particles. Our signal to noise ratio can be quite low, can be all the way down to 0.05. Here's an individual micrograph or a particle that's been boxed out and inverted, so you can see a light protein on a dark background. What we do computationally is align them, average them so we get higher signal to noise, and if we have good angular coverage, we can back project and calculate a reconstruction at near atomic resolution. As I briefly mentioned, the real push for resolution has come about from these detectors. Here's an example of a virus. Here's a cryo-electron micrograph. I stated that we are now taking movies, and the advantage of that is that we can do motion correction as well as we can gain a lot of information. So here's an example of what one frame of our movie might look like, and through taking and summing the entire movie, we can get more and more signal. However, one must take note as you can get radiation damage if you have so much electron beam hitting your sample. You can make free radicals that can break covalent bonds. Not only that, you can add enough energy that you induce conformational change. So what we can do is we can do motion correction and gain back, and we can also decide to downweight later frames such that we can lessen the contribution of the radiation damage. And we showed a couple of years ago that you can reach sub-3 angstrom reconstructions. Right now, I believe we're either 2 or even sub-2 with single particle techniques. And the reason why people find that really interesting is that you can start seeing conformations or rotamer conformations, stereochemistry, coordination. So the next section is 2D crystallography, and that is still quite used heavily. We have a bond from Mount Sinai and Hernando from Yeshiva, well, actually it's Montefiore, Einstein, talking about that. And up until a few years ago, how we routinely were able to get to near atomic was by forming ordered 2D arrays. I think about over a decade ago, the highest resolution aquaporin structure was sub-2 angstrom, like 1.9-ish, and that was done by 2D crystallography. So in terms of atomic resolution or near atomic resolution, EM has done that decades ago. The problem was that only if your sample was amenable to it. And particularly membrane proteins naturally like to go into membranes and form ordered 2D arrays. But some people are interested in filaments, and that's just a 2D crystal wrapped around itself. And why that's interesting, like if you're interested in actin, myosin, those interactions, there are many naturally occurring filaments within the cell that people have been getting near atomic resolution for years. So this is one of these tried and true techniques. Something that will not really be discussed in this lecture, but we're moving towards. There is another technique using diffraction, that's micro-ED, and a lot of crystallographers are interested in that because you can form microcrystals, and then you can use the electron microscope just by taking out the projection lenses as in diffraction. So you can take electron diffraction images and go through the same X-ray crystallography packages. And with that, people have shown within the past few years you can get atomic resolution with biological samples. Again, with material science, many of these techniques have already been worked out, and you can get atomic resolution when you have high doses. When you have biological samples, you have to be a little bit more cognizant about doses and treating your sample. And so the exciting part is that in the recent few years, by a variety of techniques, we've been getting to near atomic. Okay, and the last section of the course really is taught by a team of people that have been working on extending the EM technique. We'll have Kathy Lawson from the EMDB. So you X-ray crystallographers might know the PDB. When you work on data deposition and validation, the database is the EMDB. And this is going to be very useful because as you're reading papers, you would want to see the reconstruction, you would want to see the preliminary data. We have a challenge that our raw data, well, do we want to save the raw data in an archive or not? Our raw data, if you look at some of our direct detectors, we average somewhere around 1.5 terabytes of raw data per microscope per day. And that becomes a challenge if you just want to get the raw data and reprocess it, because there's very little data reduction. Our data, our images, and you can only reduce images so much. Something along that's been a recent issue, Tom Walsh from Rockefeller is going to talk about validation methods. And the question really comes, a lot of people want to have a particular number. Like, oh, my map's at 3 angstrom resolution. What does that really mean? In single particle, there is some debate. Also, you're talking about EM in general. Well, what does resolution really mean for a tomogram, right? Because you don't have a cubic voxel, it's an anisotropic particular voxel. So depending on which modality, there are different ways of validating that and reporting resolution. The main thing is that if you're trying to answer a question, and let's say you know at 3 angstrom resolution you can solve that question, do you have enough validation methods and a way of reporting that such that a person knows that there are a particular resolution range that can answer their question? If they know in X-ray crystallography that their question can only be solved at 2 angstroms, then how do we report statistics to a reader to know that this EM map is comparable resolution, as it were, such that they can solve their question? And that is still very outstanding. And then moving towards, as we're getting near and near atomic, people want to fit atomic models. EM maps are very different than X-ray maps, maybe not so different depending on how you look at it, but we don't have anomalous signal, as it were. So imagine if you have an X-ray map and you don't know the locations of all your methionines. Let's say you can't do a cell net, or you can't do a metal soak. So let's say you don't have a way of registering your particular protein and you have a lot of loops. That becomes quite a bit of a challenge to make sure you're not slipping register. And there's a combination of ways that we're trying to address that, but that still is an emerging field, and Ollie Clark from Columbia is going to talk a little bit about that. Okay, so that's the EM course. This is a relatively short course in the organization. Do people have any questions so far? People online can tune off afterwards, because what I'm going to do is switch gears after this, tell the people here a little bit about the Simons Electron Microscopy Center, because all of you are from member institutions. You can make use of the center. And we'll go on a tour of the facility, and not just the Simons Electron Microscopy part, but the whole NYSPC, so you know the resources available to you. Okay. Well, the people online, thank you for your attention. And I'll switch, we'll continue the live stream, but I'll just switch over to more of a sales pitch, in the sense that everything that I mentioned before about the 3 different modalities of EM we do here at the center, and we can help you. So not only do we focus on molecular structure, looking at static things, but things that are in motion, things that have conformational changes. We look at cellular structure. We do have look at things, well, these are just for fun, but we have looked at organisms. So when I say the scale is from near atomic to millimeter, we have imaged a whole C. elegans embryo that was 3 millimeters in length. It took several months, but we can do it. So when I mean that full scale, we have done that full scale here. Okay, so the Simons Electron Microscopy Center, the research here is driven by our 9 member institutions, as well as we have a P41 on site, NRAM, the National Resource for Automated Molecular Microscopy, and the Simons Foundation has been very generous with us, and that's why we've been renamed the Simons Electron Microscopy Center. So as I mentioned, we handle all different types of samples, from whether it's heterogeneous to homogeneous, and we'll go on a tour and we'll show you all the microscopes we have on site. We have, pretty much in the first or second quarter of this year, we'll have 3 up and running Titan Krioses for users to make use of. And they're a little bit different flavors. So you have access not only to instrumentation, but training and a bit of computing. If you want to start a project at the center, make sure you visit our site, semc.nyspc.org/start. Every institution, member institution, has an institutional representative, and they're your main point of contact. The educational outreach we do, this forum for this course is primarily to give you theories and concepts behind EM. This will give you appreciation of different techniques. Tomorrow, actually, we have the first round of our computational practicals. So the EM course is more theory. Practically, how do we do data processing will begin tomorrow, and that's done in 3 parts. Part 1 and 2 are on single particle. Part 3 is on tomography, and that run 1 workshop per month. So January is part 1, February is part 2, and then March will be tomography part 3. Okay. The third part of using the facility is really how do you collect data? How do you, once you have a sample, how do you use the microscope? Through new user orientation and our one-on-one sessions, we'll teach you how to use the microscope. In addition, we have quite a bit of individual outreach. We have distinct time set aside to talk to you about your project. You probably heard me say this many times for those sitting in the room. Monday at 11, or Thursday at 3, or Thursday at 4. If you email us, we can set the appointment. Us refers to emg@nysbc.org. Our EM directors, co-directors are Bridget Carragher and Clint Potter, and I'm joined by very highly trained staff that can help you and move your research program forward. The reason why I say research program is that I hope that it won't be just a one-off, because it's very easily, if you have a sample, we can give you like figure 1 and 2 of your paper. But what we hope is that this technique will become very useful, that you'll learn it, and then you can actually make use of it routinely. And then many of the people within the staff I've already outlined and showed you, they're going to be here teaching the course. The instrumentation we have at the center, currently we have 7 electron microscopes. We have 1 dual beam fib SEM. We have 2 screening scopes, a Joule 1230 and a T12. The 1230 has a 4K CCD, the T12 has a 4K CMOS. We have an advanced screening / data collection microscope, primarily for cryo and some tomography. That's the F20. It has both a 4K CMOS and a direct detector, a DE20. We have the 3 main direct detectors on site. DE makes a direct electron detector, FEI makes the Falcon, and Gatan makes the K2. We have 3 Krioses on site. Krios 1 has been up and running for a year. We have both the Falcon 3 direct detector and the K2 on it. That's just the normal Titan microscope. Krios 2 is just coming out of testing. Perhaps within the spring we'll be able to get out of beta testing. That has a CS corrector, phase plates, and an energy filter. Krios 3 was bought by Columbia. We have half the time on that, and that has phase plates and an energy filter. Right now it's a Falcon 3, and K2 possibly going to be upgraded to the K3. Okay, so that's a little bit about the center, and then what we're going to do next is we're going to have a tour. I will caution you, we're going to go through certain areas that with high field magnets, so if you have anything that you don't want to get demagnetized, you can leave it in this conference room. Okay, any questions so far about the organization of the course and the scope? Yes?
So the question on the Wednesday video screening.
Yes, that is optional. If you wish, you can always go to YouTube or go to Grant Jensen's webpage and watch the lectures.
Okay. Yeah,
But the intention would be, if I didn't really hit this home, would be that every topic Grant Jensen has a lecture on, you would watch that before coming to the lecture, such that you have the background information. And then when you get to the lecture, then it can be really an interactive lecture. Versus the problem of having an interactive lecture, if you just listen to or hear the subject the first time, is you don't have enough information, or you won't know the topic quick enough to ask any questions. So the hope would be if you watch those lectures, then it'll be good. Now, yeah, to your point, yes, you can watch that on your own, and you can skip the Wednesday session. For those, we offer it on Wednesday for those who just can't make time, or they think, oh, I'll always watch it, and they never do. So we offer a distinct time, so there's no excuse. Okay, well, I'm hoping, I didn't actually log into YouTube, so I don't know how many people are online. If there's any comments in the chat, I can log that on. Oh, 3 people are watching. And I'm a little bit delayed. Okay, nothing in the chat. Okay, so for those that are already very well versed in the center, you don't have to stay for this, but for those interested in having a tour, please come up here and then we'll head out. The tour will be really quick, it'll be only 15 minutes. Okay, so then we'll see you Wednesday for those who want to have a video screening. Otherwise, next Wednesday will be the next course, and that'll be on sample preparation and challenges for biological EM. Just don't forget, Monday is Martin Luther King, and that's a holiday.
Which we do both of these?
Oh yes, you can either get the surveys to me or place them on the back table.
Can we bring the questionnaire tomorrow?
Oh, you can bring the questionnaire tomorrow if you're coming to the Appium Workshop. For those attending the Appium Workshop, Appium Part 1 is tomorrow at 10 a.m. and that covers the basics of Appium, basically from micrographs to initial reconstruction if we have time.
How many registered for that?
Registration is now closed, but if you've already registered for it, then you should be informed. We might have space, so you can, if you don't mind being in a crowded room, you can come. You just might not be able to do all the interactive parts. The Appium Workshop is where you get a test data set, and we try to go through everything.
At what time is this?
It's 10 to 4. There'll be lunch served. They'll be here. They'll be here. Lunch is just pizza, so if you have dairy allergies or your gluten allergies, then you might want to find other options.
Should we bring our laptops?
You should bring your laptops that's capable of web browsing, and ideally we're going to set up a router, so if you have your connector to plug into the Ethernet cable, that'll be better. We've had issues when we've had 10 or so people here, 10 laptops on Wi-Fi, 10 cell phones on Wi-Fi, and who knows what, and all of a sudden we run out of ports. So we prefer, if possible, to plug in as much as we can. Okay, so for those interested in the tour, meet me and we'll head out. Thank you. Appium is tomorrow. That will be primarily if you're collecting data at a microscope here, you'll be getting micrographs. And that's what do you do with those micrographs? So that's the part 1. Part 2 is on reconstruction. So that's the further along single particle workflow. You want to make a 3D reconstruction. Part 3 is, let's say you collected a tilt series. How do you process that data?
So tomorrow is just.
It's part 1. It's basics on you collected a micrograph on the microscope.
Just like
What do I do with it? Particle picking will be covered. A lot of the web user interface will be covered. Project management will be covered. So literally it's basics in general if you want to use Appium. So that's a very useful course if you haven't received that already. Okay, so let's go on a tour. How many people are here on the tour?
It's north, so it's like 168th Street, so it's like up in the other top.
Okay.
There.